Welcome to this explainer. I am absolutely thrilled to have you here today because we are going to unpack the incredible grand mechanics behind eclipses. We're going to look at exactly how these massive celestial events work, breaking down the basic physics of light and shadow, and showing you how the universe orchestrates this absolutely breathtaking cosmic dance. So if you've ever looked up at the sky and wondered exactly how the sun just seemingly disappears, well, you are in the right place. So let's kick things off with a question. What actually happens when the massive celestial bodies in our solar system just get in each other's way? I mean, imagine being completely enveloped in the shadow of a giant planetary body that's literally blocking out the very source of our light. It's a pretty profound thought, right? And it's really all just a matter of perfect, magnificent timing. Here is our roadmap for today. First, the science of shadows. Second, unpacking solar eclipses. Third, understanding lunar eclipses. Then, we'll be modeling an eclipse, and finally, predicting the cosmic dance. Okay, let's dive right into Section 1, the science of shadows, light, opacity, and blockage. It really all starts with opacity. An opaque object is, simply put, an object that will not allow light to pass through it. And because that light is blocked, a shadow forms when that object is placed in front of a light source. This is the foundational science for literally everything we're going to cover in this explainer. Picture this. You're standing out in a bright, green, grassy field on a gorgeous sunny day. Suddenly, a massive airplane passes directly overhead. For just a brief second, you're plunged into darkness. Why? Well, the airplane is made of metal, making it an opaque object. Because the light from the sun cannot reach the ground right where the airplane is blocking it, that area looks dark. But the grass all around it? That stays bright because the sun's light is still hitting those spots. What's super interesting here is the light itself. Light travels in completely straight lines, which we call rays. These rays hit the airplane and just stop. Because light travels in these rigid, straight paths, it can't just curve around the metal body of the plane. That straight line geometry is what perfectly shapes the dark silhouette you see down on the ground. Then, when the airplane passes, the shadow just moves right along with it, and boom, the area is bright again. Moving right along to Section 2. Unpacking solar eclipses, when the moon takes the stage. So what exactly is a solar eclipse? Well, it happens when the moon comes directly between the sun and the earth. And I really want you to think about this. This is the exact same physics as that airplane we were just talking about. The moon is just a massive object made of solid rock, which means, yep, it's an opaque object. When it moves directly into the path of the sun's rays, it blocks them and casts a giant shadow onto the earth. But here's the thing. That shadow isn't the same for everyone down on Earth. In the very absolute middle of the moon's shadow, all the light rays from the sun are completely blocked. If you happen to be standing there, you experience a total solar eclipse. It literally gets dark during the middle of the day. But if you're a bit further away from the center of that shadow, some of the light rays from the sun can actually still reach the Earth. This creates a partial solar eclipse, where it looks like just a chunk of the sun has been blocked out. And this brilliantly illustrates that whole progression. As the moon gradually passes between the Earth and the sun, it kind of starts as just a small bite taken out of the solar disk. Then it progresses into that stunning, famous ring of a total eclipse, and finally, smoothly continues on its way, bringing the light back. Now, a very common question comes up right about here. If the moon takes roughly 27 days to orbit the Earth, why don't we have a solar eclipse every single month? Good question, right? Well, the absolutely crucial point here is that the moon's orbit around the Earth isn't perfectly flat. It's actually tilted slightly. It doesn't exist on the exact same plane as the Earth's orbit around the sun. Because of this slight tilt, getting a perfect straight-line alignment between the sun, the Earth, and the moon is actually quite rare. Most months, the moon shadow just completely misses us, passing just above or just below the Earth. Section 3. Understanding lunar eclipses. Earth casts a shadow. All right, so a lunar eclipse is basically the flip side of the coin. This occurs when the Earth itself comes exactly between the sun and the moon. Just like the moon, our Earth is a giant opaque object made of rock and water. So the Earth blocks the light from the sun and casts a massive shadow out into the darkness of space. When the moon's orbit happens to take it directly through that shadow, that's when we see a lunar eclipse from down here on the ground. Let's just put them side by side to really lock this in. A solar eclipse is when the moon blocks the light from the sun, casting its shadow on the Earth. A lunar eclipse is when the Earth blocks the light from the sun, casting its shadow on the moon. It entirely depends on who is stuck in the middle of this grand cosmic lineup. Moon in the middle? solar eclipse. Earth in the middle, lunar eclipse. Which brings us to section 4, modeling an eclipse, recreating the cosmos in the classroom. Look at how the curved shadow of the Earth slowly bites into the bright surface of the moon over time. It's really a majestic sight. And the incredible thing is, the physics driving this awe-inspiring event are simple enough that we can easily recreate them in a standard classroom or even just hanging out in your living room. So to model this yourself, it's actually super simple. First, just grab a standard electric lamp in a dark room to represent the sun, and set a white soccer ball on a cup to act as the Earth. Next, you'll want to attach a string to a tennis ball, which is going to be our moon, so you can hold it dangling from above. Now, move that tennis ball directly between your lamp and the soccer ball. Boom. You will instantly see the shadow cast onto the Earth. You just made a perfect miniature solar eclipse. Then, if you move the tennis ball around to the other side, right into the shadow of the soccer ball, well, you've just created a lunar eclipse. It is such an incredibly direct, hands-on way to really grasp the mechanics of what's happening out there in space. Finally, Section 5, predicting the cosmic dance, the math and history of the stars. You know, the human drive to understand our universe, it is definitely not a new thing. In fact, Middle Eastern astronomers were making the very earliest known predictions about when eclipses would happen roughly 3,000 years ago. Think about that for a second. Doing that without modern computers, without advanced telescopes, they did it entirely through careful, super meticulous observation handed down over generations. And the secret key to their predictions? The number 223. These ancient astronomers somehow realized that the pattern of solar eclipses actually repeats precisely every 223 lunar months. By recognizing this vast, cyclical rhythm hidden in the sky, they could actually project forward and warn people when the sun was about to go dark. Because, just imagine being around before these predictable patterns were common knowledge. An eclipse was a profound and honestly terrifying event. Picture being on a chaotic battlefield or in a bustling ancient city, and suddenly, the day turns into this eerie twilight. The air instantly cools down, and a black disk ringed with fire literally replaces the sun in the sky. No wonder it was almost always viewed as an intense omen or a direct message from the gods. Check out this fascinating historical record. It tells us that there was a battle in Greece in the year 585 BCE, and people recorded a total eclipse happening right in the middle of the fighting. Now, because the mechanics of eclipses operate like a giant, perfectly tuned cosmic clock, modern scientists working today have been able to calculate exactly when past eclipses happened. By matching our astronomical math to this old historical record, scientists were actually able to pinpoint the exact date of that ancient battle, May 28, 585 BCE. Physics literally solved a historical mystery. How cool is that? Today, we can predict these things thousands of years into the future with absolute precision. But I want to leave you with this final thought. As we predict eclipses deeper and deeper into the future, how will the accuracy of our predictions hold up over vast, unimaginable scales of time? Because we know nothing in the universe is perfectly static. Orbits can subtly shift over millions of years. It really just highlights the incredible, ever-changing cosmic dance that we are all a tiny part of. Thank you so much for joining me on this explainer today. Keep looking up.